This is going to be the last PowerPoint for this for kinetics, and I'll get out the worksheet very soon after I post this. Okay, and then I will post on the announcements what needs to be done. So further our investigation. One of the things that we want to do now is, so we when I was to take a look at these, we looked at rate is going to be equal to the rate is proportional to concentration. We said it's proportional to temperature. We said it's proportional to how things connect, okay, and several other things. And what we did in previous couple slides is we basically just said rate is only dependent on concentration times some constant, right? K, rate constant. And that rate constant was dependent on temperature. And actually, it had other factors involved with it as well. And what we want to do is look at K and temperature now, and see how their effect is on rate. So reaction rate depends on concentration of reactants and temperature. Collision theory based on kinetic molecule theory. That just means is that the particles can crash into each other. We related that when we talked about gases. So the central idea is the greater number of collisions per second, the greater the reaction rate. Okay, that kind of would make sense. The more it's just more available for a reaction to take place. And there's always a minimum energy of collisions needed to take place. And once that happens, it kind of just takes off. And they often the molecules have to be collide effectively. They just can't glance off of each other. Sometimes they have to smash each other into a very specific way. Okay, maybe we have two particles that look like this. Right, this guy has to go smash into this guy just like this. If it came around and hit it like this, it wouldn't be good. Okay. All right, so these are all going to be involved with our K in our reaction. Right, as the concentration reactants increase, the number of collisions increase, the rate increases. Makes sense. As temperature increases, the speed increases. Okay, remember we said is that the kinetic energy of molecules and atoms are equal to Boltzmann's constant times temperature. And this is kinetic energy, basically, if you've done physics. So, which is kinetic energy form is 1/2 mv squared. So you can see that velocity and temperature are related to each other. So if you increase the temperature, you'll increase the velocity of the particles. Okay, so there'll be a higher proportion of collisions, and because they're moving faster, they probably they'll have more energy. Not probably, they will. There'll be more collisions per second, and that increases the rate. Okay, and again, we you have to take into account effective collisions. All right, it just can't be just random collisions. All right, so we have an example here. H2 and I2 will come together and form HI. They undergo 10 to the 10th collisions per second, but the reaction actually takes a very long time. And why is that? Is because they're not effective. Okay, they're not hitting each other the right way. So not all chemical reactions will be. If you speed them up or change the concentration, they may not. That actually may not affect the rate because of this ineffective colliding. And here's just sort of an example of this, okay? Is that they have to be in the right orientation to collide. Temperature greatly affects rate, okay? And the reason why is that when we look back at Boltzmann's Boltzmann-Maxwell distribution, is that if you increase the temperature, you increase more particles that will have effectively the correct energy for the reaction to take place. Okay, and that's what we're going to be looking at here. Is that this guy here. Is that there is a effective energy that the reaction really will take off, and that's called the activation energy. So molecules must possess a certain amount of kinetic energy in order to react. So the activation EA, or sometimes called the energy of activation, is the minimum kinetic energy needed to react to occur. And get energy from collisions with other molecules. If they move too slowly, too little kinetic, and they'll just bounce off each other, not causing reaction. Without the minimum amount, the reaction will not occur, even with the correct orientation. So there is a minimum energy called the activation energy that is what you needed for the reaction to take place. Okay, and we're going to see in a second is that so when a reaction, so let's see if your starting point we're going to take a look at this more in depth in a minute, but let's say this is and this is time here. Okay, let's say this is your initial reactant. Okay, what you have to do is you have to give this guy, for it to turn into a product down here. Okay, first of all, there's a minimum energy that it has to be pop up to. Right, and once it gets to that, it'll come streaming down. Okay, and that'll be the activation energy. Okay, transition state theory used to explain details of reactions, what happens when reactant molecules collide, potential energy diagram, which I just showed you, and we'll show you how that works now. Okay, so what you do is, so here's your reactants. So let's say we're just going R to P. Okay, and we'll be looking at exothermic reaction. Okay, so this reaction will give off heat. All right, and then we call this potential energy diagram. So we're kind of looking, potential energy can kind of be associated to enthalpy. So we could replace a potential energy with enthalpy. It will give us the same kind of graph. So here's potential energy of the reactants. So what you have to do, you have to give the reactants a certain amount of energy for the reaction to take place. Now if we were to take a look at what happens to the reaction as they go to product, you'll see them actually change. Okay, and not only will they change their energy, but the reactants will change. And what they'll do is they'll turn to this thing called the transition state that we just had on the last state. So this guy up here is some species that maybe looks a little bit like the reactant in the products. And so it takes a certain amount of energy to get there to make that guy. But once and that's called the activation energy, or the energy of activation. Okay, and once that takes place, the reaction will fly down and make product. Okay, so if we look at the total energy involved, so you had to add this amount of energy, and then you gave off this much energy overall. So the net energy is going to be this right here, which is this here. Okay, we're not going to have to worry about that. But just know is that this energy that you put in, all this energy up here, when all said and done, you don't even know what had happened. It's like when you take a piece of paper and you light it on fire with a match. Well, the match's energy, you don't even know it's there when you get done burning your paper, because the paper's energy that's burned off sort of gets rid of all that, okay? So the amount of energy of the match that you lit, so that's right here, is canceled out by all the burning that was given off from the burning of the paper. Okay. So overall, when you look at the beginning and end, it doesn't even look like you added in or energy, okay? Because they cancel out. But you still need to add it, all right? Okay, and again, this is the exothermic reaction I just showed you. And delta H will be negative. Typically, we don't call it time on the x-axis. We call it reaction coordinate, because the time can change. So what we actually kind of do is look at what happens to what the reactant looks like as it moves. So we might take a picture of it here, take a picture of it here, 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 and picture of it here, and then that's what we do is we graph that. Okay. Okay, so let's look at an endothermic reaction. So okay, so delta H would be positive. All right, hope you remember this from Chem 121. So here's your reactant down here. Again, you still need to add energy, and this is not the endo part of it. So you add energy to get to the activation. So this is the activation energy. And then it flies down again, all right? But it doesn't go as far down as it did before, okay? All right, so now what happens is that you have your energy activation, and then you have your product. So the overall, from the reactant to product, is, so you add energy, and then some of it comes down, okay, but not all of it. So some of this energy here that was added came from the activation energy, okay. All right, so don't just know that no matter what you need to do for reactions, you always have to go over a hump, and the hump might give you to a lower exothermic reaction, or it might give you endothermic reaction where the product has a higher energy than the reactant. Okay, so endothermic reaction can be written as R plus heat gives me product, or R to P, where delta H is positive. Exothermic reaction, which we just did, could be written as R to P plus heat, with the delta H of minus, okay. Both of them have energy of activation that you can't see in the delta H. All right. So there's no, by measuring the heat of reaction, you can't figure out the energy of activation, but you still need to do it. Okay, so what is needed to get over that barrier at the top there? Well, you need to make a transition state or activated complex. Here's just an example. You might have you have this guy here, and what has to happen is that these guys have to swap places, and then this would be your intermediate, okay, or your activated complex at the top here. And it takes quite a bit of energy to make that. But once it makes this guy, the reaction goes downhill and makes your product. Right, and here's another example. Okay, so we started out with these two guys. They have to make the transition guide, which are activated complex, which takes quite a bit of energy, but once it makes it, okay, the reaction flies down and it gives off way more energy than was required to make this transition state. Okay, so there might be quite a bit of energy to get to the top here, but once it makes it, it's all worth it because it come back down. And here's the steps, and don't worry about it, just kind of walk through it. Okay, so what we want to do is actually measure this activation energy or energy of activation. So, so what we're going to do, and it's so getting to the top of that, all right, is actually will affect how fast our reaction takes place. So if this hill is really high, our reaction will be slow. Okay, because it requires a lot of energy. If it's low, the rate will be slower. Okay, so the rate will be dependent also on this activation energy. And so we'll look at the rate constant, all right? So the rate constant is going to be related to this, we call this Arrhenius equation, is going to be dependent on the activation energy. Right, and I don't have the method on how this was solved, but here's the equation. Is that the rate constant, the same K that we've been talking before, is equal to A, which is kind of like frequency factor, it's called, but it's sort of like the collision effectiveness of reaction. Okay, so if this is really high, then K will be high, all right? And so this has the same units as K as well. R is the gas constant, and it kind of just gives them the particles, tells how the particles randomly move around and smash into each other. EA is the activation energy, and T is the temperature. So if we take a look at this equation here and see how they're all related. Okay, so if you look at this guy up here, it says minus EA, okay? So we're going to find out that, well, let's look at temperature. So if temperature is in a denominator, okay, that means that's going to increase. So if you increase T, okay, that's going to change, well, I mean, we'll have to have to look at this whole equation, but basically if you increase T, it'll increase K, all right? If you increase EA, it'll decrease K, all right? You can see that there's a negative EA here, so a negative EA would decrease K, all right? Negative makes this a fraction, and so a high T, because it's in the denominator, will make this bigger. A minus E will make, a high E will make it smaller. So the relationship between K and in the formula is that if you increase EA, the rate constant will go down. And that kind of makes sense. Higher EA to slow the reaction. Also in this equation is that from it is if you increase the temperature, okay, you will increase the T. The rate constant, right? And also if you increase A, it will also. And so that's all derived with that in mind. So just know those are the relationships. Okay, so what we can do is take this equation and actually make sense, and what we can do is actually figure out what this value is of what the activation energy is by varying the temperature and measuring K. All right, and so I mean, and what we want to do is use a plot to do that. So one thing we can do is rearrange this equation, and all you do is take the log of both sides, and then you would get this. And then what you can do is rearrange this guy here so it looks like this. Now why would we do that? Well, what we can do now, what we have is y equals oops, this should be 1 over t here. Y over m x plus b. Okay. Y will be the log of k, and x will be inverse of temperature. And then our slope will be m equals minus EA over R. And then we know R, that's the universal gas constant. And so you can solve for EA. And so you get EA equals minus slope times R. Okay. Also, you can figure out A, because that'll be the y-intercept. Okay. So what you do is you plot the log of K, x-axis, over the reciprocal of t. Hopefully, it'll get a straight line. And when you get that straight line, you'll get a slope. And then from that slope, you can find the energy of activation. So let's look at an example here. All right. So here's some data. And you can figure out, this will be a lab actually that we do, is that so you have temperature, and then you can figure out the rate constants at different temperature. Okay, so in the previous slide we had ways of figuring out the rate constant, and what we would do is figure out the rate constant for that same reaction at different temperatures. And so that's what we do here. So this is your raw data. All right. Okay. So the next thing you do with the temperature is you make sure it's in Kelvin. And then you take the reciprocal. And this data here will be your x. Okay. Now your rate constant is here. And then you take the log of it, and then it no longer has any units. Okay, so this will be your y. So you plot this versus this, and this is what you get here. This curve. Then simply you have the slope. Okay, m. And equals minus EA over R, and then we could solve for EA. And also this point right here is the Arrhenius constant. Okay, you take 2 points on that line, okay, or you could just simply use a calculator to figure out the slope. And I mean, just put in the data and you have it come up for a slope for you, and then and that's how I would do it. I would just put the data in my TI 45 or whatever. Do the calculations that finds linear regression, and that'll give me my slope, and that'll give me my intercept. Okay, I mean, you don't even have to graph it. You can just plug it in your calculator and it will give you your slope and your y-intercept. And then, so the old-fashioned way is to do it with the is actually plot it out. So so you won't have to plot it out unless I tell you to do that. But anyways, you could do it like this. You could do it that way, or you could do it from your calculator. Anyways, you get a slope. This is the slope. All right. And then then you multiply it by r, and also by negative number, and you'll get your EA. Okay, so that's what we did here. So we took the slope, multiplied it by r. Now the r is going to be specific in terms of joules per mole. The universal gas constant that we've used before is 0.0821 liters per atmospheres per mole kelvins. Okay, all right. It also can be written in terms of joules per mole Kelvin. And the reason why that is that liters of pressure times volume is also an energy term. So which joules are. Okay. So we can use this value here instead of this value here. Just the units are different. Now when you do that, we get the EA is 1.01 times 10 to the 5th joules per mole. And it's positive, by the way. Tendency a lot of times is for people to leave off positive, but you should really tell which direction it goes. It's up. All right, we're done with kinetics. Okay, so what I'll do is I'll send you out a worksheet that goes over how this, and there'll be a test that relates to both the worksheet, and there'll be a multiple choice as well. Let's say I get that out to you. I'll put the announcement out when that all is going to take place. All right, so that's it.